Alright, this is AQA A-Level Physics 2023 Paper 2. As per usual, I can't show the paper on screen, otherwise AQA will copy strike my channel into oblivion like they almost did in the past. So link to the paper and mark scheme are in the description for you. Question 1.1. What is internal energy of a gas? You should kind of remember this from GCSE because, well, we know the internal energy of any substance is the sum of kinetic energy and potential energy of all particles in a substance. However, in a gas, in an ideal gas anyway, there's no potential energy because there's no attraction between the particles. There's no intermolecular forces. So we just say the sum of kinetic energy of all particles in the gas. You could say molecules, but of course it could be atoms. So yeah, particles is a better one to go with. And instead of sum, you could also just say the total kinetic energy. Nice, easy start. Next, we have a particle in a box. Explain why is there a momentum change of minus mc? What we say is momentum. Why is it c? It really should be u or v or w, but whatever. Momentum before is mc. Momentum after collision. Lots of people will say, hang on a minute, but it's still mc. But no, because it's traveling in the opposite direction, and so it has to be minus c due to change in direction, but not speed, or we could say energy. So therefore, delta p, change in momentum, is equal to mc minus mc, and so that's equal to, well, fine, whatever. We should really do after take away initial, so therefore that's minus 2mc. But really, we're only concerned with the magnitude because, of course, that is the same on the other side as well. So this is quite a nice question, actually. We're just being asked to derive the kinetic theory equation in several steps. So, you know, not a bad start. Show the frequency is c over 2l. Well, this is because, well, frequency is equal to 1 over the time period, and the time period is equal to time taken to travel 2 lengths of box. And we know that speed is equal to distance over time, so therefore time is equal to distance over speed, or in this case, that's 2l over c. So therefore, frequency is equal to 1 divided by that. And so that is equal to c over 2l. Easy. And then, not a big surprise, we're being asked to then talk about pressure. So pressure we know is equal to force divided by area. And we know that force is equal to rate of change in momentum. So that's delta. I'm just going to put delta. Should I put that? Yeah, let's put delta little p. No, I changed my mind. Let's say delta mv over time divided by area. And so that's equal to, well, we said our change in momentum is minus 2mc over the, well, let's just say area times by time again. And so that is equal to minus 2mc over the area. Well, it's a box, a square box, or cube, one might say, but the side W is a square, so it's just L squared, isn't it? So L squared, and that's times by the time. I don't know why they said frequency before. This is a little bit silly because we never use frequency in this context. I don't think so anyway, because this is how we do it. So divided by the time, and so the time we said was this, so 2L over C. And so those 2's cancel, and the c ends up on top, and so therefore we have minus, we don't really care about the minus though, minus mc squared over L cubed, or in other words, minus mc squared over V. Is that all we've been asked? Yes, it is. Pressure is equal to minus mc squared. We don't really need the minus though. That's what I don't get, why the whole change in momentum thing has to be minus 2mc, because eventually we just drop that minus, but whatever. Okay, we have a tyre, and so that is 330 mil. Actual tyre itself is 660, so guaranteed we're going to have to take one away from the other, one area away from the other. One is double the radius of the other one, so that should indicate that there's probably going to be some proportionality that we can employ at a guess. And the width is 370. Okay, the gas is at a pressure of, should I put P1 is equal to 1.01 times 10 to the 5 pascals. Okay. More of the same gas is added. And then it's measured again. Okay, so we're going to have a P2 at some point. Oh, we do have the pressure afterwards. Sorry. Right. Let's write that down. So 2.11 times 10 to the 5. I think there's probably going to be some proportionality. So we actually haven't... Oh, I think this is going to be hard. So tell you what, I'm going to put big M. So that's total mass. Total mass 1 is equal to 14 point that. And then total mass afterwards is that. So we're just being asked for the molar mass of the gas. So we need the mass of the gas in kilograms. Remember that little m is just one molecule. And that needs to be divided by n, because that then gives us kilograms. Somebody's going to say that's a U. There we go, over n. And that gives us the molar mass in kilograms per mole. As you can see, it's kilograms divided by mole. So how are we going to do this? Here's the problem, is that we need the mass of the gas. And the problem is that, well, let's put it this way. Let's crack out our equation. So PV equals nRT. We're going to go with nRT. We're told that it is at a temperature of 100 degrees C. Let's say 273 plus 100. That gives us 373 Kelvin. That's our temperature. That's constant. So what's staying constant here? R and T are. So we can say that PV1 over N1 is equal to P2V2 over N2. Is that fair enough? Okay, so let's start off nice and easy. Let's get us some easy marks. Let's go for volume is going to be equal to... well, it's going to be the area of the whole thing, take away this area in the middle. I say area, that's going to be volume, isn't it? But we'll deal with that in a second. So we just want this area here. So that's going to be pi d squared, pi big D squared, let's say, over 4, minus pi little d squared over 4. And that's all then going to be times by the width. Can I put W there? So that's going to be, yeah, there we go. But actually we can see that our big diameter here is 2 lots of D. So I guess that could just makes things a little bit easier maybe. So we can say that's equal to pi times 2D squared. So that's going to tell you what, let's write it down. Divided by 4 minus pi D squared over 4 all times by W. And so that's going to give us 4 pi d squared over 4 minus pi d squared over 4 times by W. And so that's 4, take away one of those. So that's going to be 3/4 pi d squared. And so that's going to be the 330, isn't it? Times by W. There we go. And so putting numbers in there then, that's going to be equal to 3 times pi times by, in meters, 0.33 squared times by 0.37, and that's divided by 4. And that gives us a volume of 0.0949 meters cubed. What can we do with that then? Well, actually, if we just have a look at our equation, if we have the pressure to begin with, and we also have the volume to begin with, and we have the temperature, and we know what the molar gas constant is, 8.31, then we can actually find out the number of moles inside to begin with. That's good, isn't it? So N1, so let me just rearrange this. N is going to be equal to PV over RT. So N1 is going to be equal to, that's our 1.01 times 10 to the 5, times by our volume of, what do we say it was? 0.0949, divide that by 8.31, times that by 373 Kelvin. And that gives us 3.09 moles. Cool. So we have our number of moles to begin with. That's going to be helpful because we know we need our molar mass in kilograms per mole. So then we can also do the same for N2, the number of moles afterwards as well. I'm not sure I'm going to need that. We'll cross it out for now. So N2 is just going to be our P2, that's 2.11. Do you know what? There's actually an easier way of doing this. Oh, is there? I don't know. Maybe not. Times by, well, I'm going to need V2 as well. Oh, sorry. Man, I've messed up here. This is where I'm getting confused. This volume stays the same. So actually, this is just the volume as is. So that's quite easy. Then we can just pop in. Do you know what? We can just take 3.09 moles, divide that by 1.01, and then times that by 2.11. There we go. I mean, yes, you can do it that way if you want to, but it's a bit quicker doing it this way. So 6.46 moles. Okay, so we have N2 as well. Okay, so we found out some data. We've got the number of moles, but then the real kicker in this question is the whole mass of the gas, because we've just been given the total mass of the wheel with the gas in. So we have a difference in mass of, what do we say, 14 point... yeah, all this up here. And so that should give us something like, what's that, 0.094 kilograms. There we go, that's the difference in mass. And we also have a difference in number of moles as well. And so that's just going to be our 6.46 take away 3.09. So actually when I said we need NM over here, we don't need the number of molecules, we just need the mass of the gas divided by the number of moles. So that's good. So we have a difference in mass of the gas, because that's all it's going to be. Yeah, it's the difference in the mass of the wheel, but the only difference is the mass of the gas. And then we have a difference of 3.37 moles. And so therefore, if we're looking for molar mass, and that's in kilograms per mole, look at this, we have a difference in mass and we have a difference in moles. And so we can just take those numbers. So that's going to be this up here divided by 3.37 moles. And that's going to give us 0.028 kilograms per mole. You know, this is why this question is mean, because if they'd said calculate, if they'd said, first of all, calculate the difference in moles, that wouldn't have stopped you from testing your physics ability, but it just would have actually stopped the insane amount of inference that needed to happen. In fact, AQA have a couple of weeks ago, actually, before making this video, they said that they're looking at the recent papers and they're going to make the papers a little bit more accessible. I can guarantee that it's this kind of question that people were making us think about justifiably. It's the insane amount of inferences that you need to make. It's just, here's some data and then bish bash bosh 5 markers. It needs to be a little bit more structure, and in fact that's what AQA said, and it seems like somebody at AQA has finally sat up and listened to people like me who have been ranting for the past few years, saying that these questions aren't necessarily testing people's physics ability, they're just mean, and whether you get what the question is asking you or not often is just down to pure luck. Okay, 2.2 motorsport regulations, blah 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 blah. The amount of gas is checking the pressure, blah blah. The regulation maximum temperature for the tyre when making this measurement. Explain why a maximum temperature is specified. Well, that's because temp increases during the race and therefore pressure also. If test carried out at lower temp does not check if tyre can withstand pressure during race. Can't stand the pressure, man. It's almost like, I guess we could say, higher temp simulates pressure when more gas added. There we go, something like that, I don't know. Okay, moving on. 3.1. 2 properties of a radial gravitational field. Field becomes weaker, or we can say field strength decreases with distance. And we can say, because we know G is equal to Gm over R squared, we can say that G is inversely proportional to R squared. So inverse squarely, or inverse square relationship. And also, unlike electric fields, it's always attractive. Or is that just because we haven't found negative gravity yet? Ooh, controversial. I don't know. Okay, space probe is launched. We have a... What do we have? We have a... Let's draw it over here, actually. F against H. Ooh, it's H above surface. Always be careful with that. So they like to catch you out. It always catches me out. Okay, state the physical significance of the shaded area. Okay, so we know from our equations that if you see my video, I do them in a nice loop. Really worth thinking about your equations in those terms. So F is equal to GMM over R squared. But we know that work done is equal to force times distance, or FR. So that means that if we go round to our next equation on the right, again, if you see my video, they might go in a nice cycle like this. And there we go. Why do I do it that way? Okay, this means that we have potential energy because it's GMM over R. And so therefore, this here, to all intents and purposes, if we're talking about a change in height, that is the same as a change in distance from the center. And so therefore, area under graph is equal to change in potential energy. There we go. Because an area is the thing on the y times the thing on the x, and so you get the idea. Make sure you have change in there, though. It has to be change in. Mark Scheme says that we need to go from the surface to a height of whatever. I mean, you know, that's dumb because, yeah, they better not mark you down if you don't put that. That would be absolutely ridiculous in that. But it wouldn't surprise me with AQA because they are that flipping vindictive. Okay, so we have GS and GE. We're just being asked to do that. Okay, calculate GS by GE. Now, whenever it comes to a question that says calculate this ratio here, you know that all you have to do is replace the things that you have with something that they're proportional to. That's all. That's what all these questions are. So we know that G is equal to big GM over R squared. Now, what do we know is staying the same for the Sun and the Earth? Well, it's just going to be G, isn't it? Because M is going to be different and R is going to be different. So therefore, we can say G is proportional to M over R squared. Okay, so therefore, we can replace G on both the top and the bottom with their M's and R's. So I'm going to say the mass of the Sun divided by the distance, sorry, not the radius, distance to the Sun squared. And then that's going to be divided by the mass of the Earth divided by the distance to the Earth. That's going to be squared. And then what you can do in this case, in all these cases really, is then say, well, that's the same as, you put the same terms together. So we're going to say that's the mass of the Sun divided by the mass of the Earth times by the reciprocal of what's going on with the radii. So this ends up going on top, doesn't it? And so that's going to be the radius of the Earth divided by the distance to the Sun squared. And then we can go one step further. We can say that's the ratio of their masses times by their distances all squared. The ratio of the distances all squared. So that makes things a little bit easier. It so happens that in this case we are talking about the radius of the Earth, aren't we? Because we're talking about what is the ratio of them at the Earth's surface. So that's kind of nice. So we're going to say that's equal to, I'm going to have to get my formula sheet, aren't I? Okay, mass of the Sun, that's 1.99 times 10 to the 20, is it? No, 30. Good grief. He's a big boy, isn't he? Divide that by the mass of the Earth. Let's cancel some powers of 10 down. Let's just call that 6. Why not? Doesn't really make a difference, but there we go. And then we're going to times that by the radius of the Earth we said was... Wait, are we told that? So, no, we're not. So we do need the mean radius. And so that is, according to the formula sheet, that is 6.37 times 10 to the 6. And then divide that by the distance to the Sun. We're told that in the question, 1.50 times 10 to the 11. And that's all squared. Why not? Let's cancels from powers of 10 again, so 6 on top, 11 on the bottom, so it's just going to be 5 on the bottom. Cool. And if I was really cheeky, then I could take the times 10 to the 10 out, because it's squared. That's going to be divided by, isn't it? And so therefore, you don't have to do this, but I'd rather not have a 10 in my ratio. I don't know why. And so I'm just going to take that away from the 6 there. So it's just going to be minus 4 on top there. Let's give that a go. So I'm just going to do 6.37 divided by 1.5, and that's squared. And then we times that by the ratio on the left. I'm just doing it a bit backwards. And that gives me a ratio of 6.01 times 10 to the minus 4. No units, because it is just a straight ratio. 3.4, I guess I missed this the first time around. Why is GS more important than GE when it escapes the solar system? So let's say at edge of solar system, we can say the distance to the Earth is roughly the same as the distance to the Sun, because it's very far away from both, isn't it? So therefore, as G is equal to GM over R squared, force or field strength due to, I guess I should say strength of field to be technically, it just sounds better, doesn't it? Due to the Sun is a lot greater than that due to the Earth. There we go. 3.5. It reaches where gravitational influence is negligible. Probe is unpowered. Okay, it's a lot of words, AQA. Just tell us what we need. Okay, let's just put our blinkers on. What are we told? The gravitational field of X changes the kinetic energy of the space probe. Okay, so we know that whatever change in potential energy we have, that's going to be equal to the change in kinetic energy. That's what we need to remember here. Okay, so we have the distance from center of mass, and we have the speed of the space probe as well. Okay, calculate the mass of X. Ooh. Okay. Okay, fine. So we have, let's say RA, that's the distance to the planet to begin with. And so that's just going to be 6. Let's put times 10 to the 6. And then B afterwards, that is 0.17 times 10 to the 6. And we have the speed before, that's 1.1 times 10 to the 3 meters per second. And we have the speed afterwards as well. Right, so what are we going to have to do with this? Well, we don't have the total distance, do we? But we do have an RA and an RB. Oh, for goodness sake. Do you know what? Screw it. I am just going to put 1 and 2 because I will never, ever remember to put A and B. For some reason, I suck at it. But 1 is A, 2 is B. All right. So what do we know? We know that we have a change in potential energy. All right. So change in potential energy is going to be equal to GMM over R1. Take away GMM over R2. It doesn't matter which way around because we're just going to end up with the magnitude. That's all we care about. Don't forget that whenever it comes to GMM over R, this is never a distance moved. So you can't just do 6 take away 0.3. This is never R2 take away R1. So get that out of your head. You have to do the total energy 1, take away total energy 2, and that's what I've done here. However, you can then factorize it, of course, and so that's going to be GMM, and then factorize that 1 over R1, take away 1 over R2. We do know the wee mass of the probe there. That's 4.9 times 10 to the 4 kilograms. All right, so that's fine. Oh, okay, yeah. So we're looking for this big M, aren't we? So we know that. So how do we know the change in potential energy? Well, we don't, but we do, or we can, calculate the change in kinetic energy, can't we? And so therefore, actually, I've just figured out we don't need this. And so we can say this is also equal to the change in kinetic energy too. What's that going to be equal to? That's going to be equal to half mv1 squared take away half mv2 squared. And so, again, we can factorize. So that's half m. So that's v1 squared, take away v2 squared. And look, we've got an m on both sides. So we don't actually need that. It will be true regardless of how heavy the probe is. And quite often that is the case, as you know, with gravity. So therefore, let's write this out nice and clean like once more. So big GM 1 over R1 minus 1 over R2 is equal to a half times V1 squared take away V2 squared. Cool. And so now all we have to do is pop in our data and rearrange. That's all right, isn't it? So we're looking for M, aren't we? So therefore, I'm going to say M is equal to, I'm going to put the half on the bottom, you think, so I'm just going to pop that 2 there for the time being. And we know that's also G on the bottom. And 1 over R1 minus 1 over R2. And then we have the V1 squared take away V2 squared. All right, let's pop in our data, shall we? So we have our V1 squared. It doesn't really matter which way around it is, to be honest. So 1.1 times 10 to the 3 squared. Do you know what? I'm not even going to do that, or am I? Let's leave it for now. So I just hate doing that. I hate doing squares on standard form. It triggers me for some reason. There we go. What a mess. I think what we can probably do, we can probably take the times 10 to the 6 off the bottom, divide by that. So divide by times 10 to the 6. So we actually end up with times 10 to the minus 17 here. And so, again, you don't have to do all this. You can just put it into your calculator if you want to. And in fact, you can just calculate change in potential energy, then whatever. I just like doing this because at degree level, this is the kind of thing that you need to do. So might as well get practicing, even if you go on to do something that isn't physics. So I'm going to say there's 1.1 squared, take away 1.3 squared, and that's all times 10 to the 6, because times 10 to the 3 squared is times 10 to the 6. Divide that by 2 times 6.67 times 10 to the minus 17, but I'm going to put that on top. So minus 17 divided by that, so that gives us plus 17 on top. So that's times 10 to the 23. And then we have just our 1 over this, take away 1 over that. Okay, let's see what we end up with. Let's see if my jiggery pokery has paid off. I'm just going to find out this bit first, actually, because I hate dealing with fractions inside fractions. This ends up being, so I'll tell you what, I'm just going to say 1.1 squared take away 1.3 squared times 10 to the 23, divide that by 2 times 6.67 times by apparently I have 5.72. There we go. Now I'm going to pop that into my calculator, and that gives me 6.29 times 10 to the 20 kilograms. Math scheme says 6.3, so it's a 2 sig figs. So I will very much take that dub. Okay, we have an alpha particle detector. So we have mesh there, and then we have blah, 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 blah. And then here now to 4,000 volts there. Okay, this is 5 mil. Okay, what are we being asked? We have P. Oh, sorry. Yeah. P is at 2,000. Right. So, okay, we're being asked to draw a graph of what is happening. Come on, give me a straight line. Yes. So that's our electric field strength there. That's our distance there. We're being asked, what does it actually look like? What does the electric field strength look like? So we know that electric field strength is equal to it's potential gradient, isn't it? And so that's delta V over delta D. So we know that the quicker, as it were, the potential is changing with distance, the bigger the electric field strength. Okay, so this is the wire here, isn't it, at 5 mil? And so we know that the potential is changing quickly at this point. So we know it's going to be highest at this point. If we look over this area here, it looks like the first 1, 2, 3, maybe even 4 lines are equally spaced apart. So it looks like delta V over delta D is going to be constant here. It's the same spacing, isn't it? And so therefore, it looks like that over the first maybe 3 millimeters, the electric field strength is constant. And so I'm going to say it's something like this. So it's going to be going straight, and then, come on, give me a straight line again. Thank you. And then it's going to sort of just ramp up there, because at this point it's going to start increasing. What we essentially have is a uniform field for the first 3 mil, at least along that line. And then as we get closest to Y from that point, it ramps up very quickly. It's going to be a radial field or similar at that point. Okay, 4.2. Oh, there we go. We have a ratio again. So speed of electron when it reaches the wire. Oh, man. Okay, so they have no kinetic. Oh, I see. So we have the ion is going up, and the electron is going down. Okay, yes. So we're looking for the speed of the electron when it reaches the wire. Oh, I should probably be careful here with my V's. Okay, I'm going to do little V's. So we're looking for the speed of the electron divided by the speed of the argon. Can I put VA? So like I said earlier, we need to know what these are proportional to. So what do we know? We know that the kinetic energy gained by both is going to be equal to EV, because that's the energy, isn't it? That's the energy of any charged particle that's accelerated through a PD, and that's going to be equal to half mv squared. So we're not going to need that there. So we're looking for V, and so therefore we can say that this should be Q, actually, come to think about it. So we're looking for V, so therefore V is equal to the square root of 2QV, big V, that is, over M. Okay, so like I said before, we have a ratio, so all we need to do is replace what the thingies are proportional to. And so, well, what's staying the same here in our speed equation? The 2 is staying the same. They both have the same charge, just opposite magnitude, doesn't really matter. And they're actually being accelerated through the same PD. So actually, they're both going to have the same kinetic energy. And so therefore, we can say that their speed is proportional to 1 over, tell you what, let's just say the square root of 1 over m. There we go. So I can say that, so VE over VA is equal to, can I just combine them all in one root? Would you mind? Thank you. So 1 over ME divided by 1 over MA, but this can end up on top. So in other words, it's just the root of MA over ME. There we go. And so therefore that's equal to the square root of mass of the argon ion, we're told that, which is nice. So there's that, minus 26 divided by mass on electron. I can remember that bad boy. And why not? Let's just sort out powers of 10. So plus 31 on top. So that just ends up being times 10 to the 5. So what do we end up with if we put that into our calculator? 6.64 divided by 9.11, square root of that. And we end up with 270. That's our ratio. Okay, 4.3, the air does affect the motion in reality. How does the presence of the air, how does it change the ratio in question 0? Okay, so the argon ion will experience more collisions, or will collide more times with air, but it's got a short distance to go. I don't know. We'll have a look in a second. With air molecules, therefore, will lose more kinetic energy over same distance. We could also say that it's more ionizing. I don't think that we need to talk about the different distances. It says that actually do not allow explanations, but I don't really get that because it has to travel a lot further. So I don't think that's very nice. Okay, so that means that VA is going to be less, and so therefore VA is less, therefore the ratio increases. Silly question. 4.4, we have a graph of force against distance. So I wonder what this is going to be about. Oh no, we're going to have to count squares, aren't we? No. Oh, that's a nice curve. So we have 10 there, and then it's going all the way to, whatever, I don't think we're going to need that. What's this, times 10 to the 3 newtons. Okay, good. We're just being asked to confirm which is which. Is it inverse square or exponentially? Super easy to prove. If it's inverse square, let me say that a bit Aussie. If it's inverse square, we know that the count rates will be proportional to 1 over h squared. So therefore, f(h) squared is equal to a constant. So all we have to do is take 2 points and prove that that is true or untrue. And so f(1h1) squared is equal to, let's just take 10. I don't think we need, we don't even need the times 10 to the 3. It's just about numbers, it's all relative. So we can just say 10 times the height is just 1 squared. That's nice. And I don't think this is going to be true, to be honest. So that just gives us 10 f(2h2) squared. Yeah, let's just go for the end. Why not? And so that ends up being, what's that, 0.6 times by 2.5 squared. Probably could have done that in my head. So that's 3.75. Therefore, inverse square is not true. Is it exponential? If exponential, then that means f1 over f2 is going to be equal to f2 over f3 for the same delta h, same increment. And so let's go for f1 over f2. So let's just go with 10 over, where should we go to? Oh, yeah. Let's just go for 1.1. There we go. Nice. So we're just going to go to, so we're just going to say 10 divided by, so going over to 1.1. So that ends up being 7 points. So we're just going across to here, and then we're going to go across to here. And we're going to see if they're the same. So there's 10 divided by, what did I say? 8 point, no, that's a lie. 7.4. If I was smart, I could have done it the other way around, to be honest. Whatever, it doesn't really matter. And so that ends up being 1.35. And then f2 divided by f3. So just 2 points. So we're going to take our 7.4 again. We're going to go over to 1.2. And that ends up being just a little bit above. I'm going to say that that is 5.7. That's not about right. Maybe slightly off, but it doesn't matter, I don't think. And that gives us 1.30. So not equal, therefore not exponential. However, it's not a huge difference, but could be. So there's not a big difference there, so it could be. Should we go for one more? Let's go for one more. Let's go for just pick 2 points further down the line, shall we? Although it's going to get less accurate as you go. So I don't know if that's a good idea. Let's go for 1.4. So at 1.4, that is definitely 3.5. And then at 1.5, that is 2.85, let's say. I'm being probably a bit cheeky there. If I divide one by the other this time, oh yeah, definitely not. So we can see that it gets further away from that 1.35 that we had to begin with. So definitely not. Cool. Okay, question 5.1. I messed this up the first time. Thank you to Captain Physics for spotting my mistake. Now we have this circuit here and we're being asked to prove that the time to charge from 2 volts to 4 volts is 0.7 R1C. Now, my instincts took over, my wrong instincts, and I know that whenever you see 0.7, you're probably looking at 0.69, which is log 2. And so I got originally the charging equation, and I just said, well, I know we're going to be looking for log 2, so therefore I can just put 2 over 4 equals that. But that's not true, is it? Yes, we can do that kind of thing if we're doing discharging, but we can't do that when we're charging. And that is because this here must be the final PD when it's fully charged. We know that this is 6 volts, and so therefore we can't put anything other than 6 volts for V0, because of course we know that the graph goes like this. And this is because essentially, whenever we use the equation for decay, every value that you put in for PD is relative to 0. And so, well, we can put in 2 and 4, etc. because it's 2 above 0, 4 above 0, because that's what the PD will end up eventually at infinity. However, when we're doing charging, the PD is going to end up at 6 volts in this case at infinity. And so everything needs to be relative to that 6 volts. So that's just silly me. I saw the 2 in the 4 and I thought, oh, well, that's going to be it because that'll give us a half. And so that'll give us log 2, which is 0.69. But that's not the case. But we can't use that because therefore that would imply that, say, for instance, if we went from 1 to 2 volts, that would take the same amount of time, which of course is just nonsense, isn't it? So therefore we have to use the equation twice. So we're going to say, just taking our equation here, we're going to say 2 over 6 is equal to 1 minus E over, let's say, our first time over RC. And then we're going to do the same for this, for 4 volts. That's our second time. And then we're going to have to find out the difference, aren't we? So therefore, I'm going to say that T1 is equal to, just multiply these out. So it's going to be minus RC log, let's just call that 2/3, why not? And then T2 is equal to minus RC log of 1/3. And we're looking for basically, well, there's our 2 volts. So that's T1, 2 volts. I've done a very good job there, but you get the idea. And then that's our T2. We're just looking for the difference. Doesn't matter which way around we do it. So therefore, the time is going to be T2 take away T1. And so that ends up being, again, we don't really need the minuses. We're just looking for a difference, so it's all good. So RC log 1/3 take away RC log 2/3. And so that's equal to factorizing. That's log of 1/3 take away log of 2/3. And using your log identities, we know that that is going to end up being RC times the log of 1/3 over 2/3. So essentially that ends up being just, well, cancelling those. It ends up being RC times the log of 1/2. And again, using our log identities, that's going to be equal to log of 1 take away log of 2. Log of 1 is 0. So that just disappears. So it just ends up being log 2 times RC. And that gives us 0.69 RC. So that's how we properly do that question. Okay, we have a graph and we have the current is thingying. Okay, so the capacitance is that. How are we going to do this? So we're looking for capacitance. So capacitor is charged until the PD across it is 4 volts. Okay, I don't think we're told anything else, are we? Interesting. Okay, so, oh no, we're going to have to count squares. Oh, I was like, oh, we need a resistance. Nope. We've only got current. We're going to have to find out charge from that. So what do we know? We know that Q is equal to VC. So therefore, capacitance is equal to Q over V. That's the OG equation, isn't it? And so therefore, we know that charge is equal to current times time, as it were. But we know that this is going to be the area under the graph. And so that's what we're trying to find out. Oh, no. And that's going up to, are we going for fully charged? Yeah. We're going for fully charged up to that 11. I mean, they're not bad squares, to be perfectly honest. Don't count the little squares in this case because there's quite a few bigger squares. So that's fine. They're not huge, the big squares. So let's say, first of all, that 1 box is equal to 1 second times by, I should probably do the charge first, to be honest. So 0.5 times 10 to the minus 5 times by just 1. And so that just ends up being, well, let's just say that's 5 times 10 to the minus 6 coulombs. So there we go. Count your number of squares. And I think you're probably looking at something like 80 squares, 80 boxes, whatever. Probably should have called them squares. Times by 5 times 10 to the minus 6 coulombs. And so that gives us 400 times 10 to the minus 6 coulombs. Or in other words, 4 times 10 to the minus 4 coulombs. So we have our charge. And oh, that's nice and easy then. All we have to do is say Q over V. So that's going to be, oh, look at this, of course. 4 times 10 to the minus 4 divided by 4. And so that just ends up being 1 times 10 to the minus 4 farads. Like the question said. Funny that. 5.3, when it reaches 4 volts, it's discharging, and then it's 2 volts, it's charging. Okay, this is a bit crazy, this graph. Determine the value of R2. Okay, shouldn't be too hard. So we have a graph when it's discharging, so we can use our whole time constant. So TC equals RC, yes, we know, equals 37% of V0. And that's going to be equal to 4 volts times by 0.37. So that is 1.48 volts. I think it's probably going to be 1. Yeah, we'll see. So we know the capacitance. We're looking for this resistance that is discharging through R2, isn't it? Oh, this is going to be R1 plus R2, actually, come to think about it, but whatever, we'll just call it R for the time being. And so we need to know this time constant, and so this is going from, it starts discharging at 11 seconds, and then to get to 1, it's not going down to 1.48. You've got to be kidding me. Oh, that's so mean. They did that intentionally. Ooh, catch him out. My days. Okay, whatever. They want to play this game. Fine. So we have to go the long way around. So we have to use V over V0 is equal to e to the minus t over RC. Like we said, log in both sides, blah, 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 blah. And so we have the log of, let's go to, 2 volts. Yeah, I mean, that makes sense. Can we use what we saw earlier? No, we can't, because that was charging. I don't think so anyway. Doesn't matter. So we have 2 over 4. So again, that's going to be just minus log 2. We'll write that down in a second. And that's going to be equal to minus t over RC, where RC is our time constant. And so we said this is just going to be log over half. And like we said, that's just minus log 2. So once again, so log 2 is equal to minus t. How long does it take? So it's going from 11 seconds to get to 2. That goes to 32. So that's just 21 seconds. There we go. So that's minus 21. Oh, I've gotten rid of the minuses though, haven't I, by doing log 2. So 21 divided by R times C. Fine, let's write that down there. We're looking for R, and so therefore swapping these round, R is swapping these round. R is equal to 21 over, fine, let's write it down. Let's just say C log 2. And so that's equal to 21 divided by 1 times 10 to the minus 4 times by log 2. And yes, I can say log 2 because it is a log. Stop saying lun, you weirdos. And that gives me a resistance of 303 kiloohms. However, this is R1 plus R2 because, of course, it's discharging through both resistors. So therefore, R2 is equal to 303. Take away, what do we say the resistance was? Did we calculate that earlier? Okay. So there's a bit of an extra step here. So we actually have to find out R1 as well. Is there a shortcut that we can do? Yeah, no, I don't think so. Okay, so yes, I think there is actually. Quite often they will be cheeky. And it was quite a while back here, wasn't it? So we said that the time to charge from 2 volts to 4 volts is 0.7 RC. Right, and that was R1C, wasn't it? Okay, so if that's the case, so we said that the time taken to charge from 2 volts to 4 volts, cheeky beggars, T is equal to 0.7 RC. And so therefore, R1C, therefore R1 is equal to T over 0.7 C. And so that is equal to, let's have a look at our graph again. On the right-hand side, when it's charging cheeky burgers, it's going from 32 seconds to 38. Sorry, 39. Oh no, yeah, that's right. So that is 7 seconds. So that's, oh look at that, it's 7 over 0.7 times by 1 times 10 to the minus 4. So that cancels, and that just cancels the 0.1. So it's just 1 over 1 times 10 to the minus 5. So it just ends up being 1 times 10 to the 5 ohms. Cool. Or in other words, 100 kiloohms. That sounds about right. So therefore, R2 is equal to the total. Take away the 100 kiloohms. I think probably margin of error and rounding error, we're probably just looking at 200 kiloohms at a guess. Or in other words, 2 times 10 to the 5 ohms. Cool. Again, very mean. If they had said, use your answer from this previous bit to do that, again, it's the, oh man, maybe I should use this little bit of niche information that I got 10 minutes earlier. It's mean. It's really mean. Okay, 6.1. Nuclear radii can be estimated using alpha or high energy electrons. 2 advantages of using high energy electrons rather than alpha particles for this estimate. Okay, we know that de Broglie wavelength is equal to h over mv. And so first off, we can say that can be accelerated to faster speeds, therefore lower wavelength, therefore finer resolution, bigger fringes and all that jazz. What can we say as well? I guess if we're talking about nuclear radius, so electrons not repelled by nucleus, unlike alpha particles, therefore can get closer. There we go. A bunch of other things you can put as well, like easy to produce, which they are, I guess. Okay, we're being asked to draw the classic graph of what we have intensity-wise. I didn't do a good job on those axes there, but it doesn't matter. But we're looking at, if we're talking about theta there, it's for our first order. It starts maximum, comes down, doesn't go all the way to the bottom, and then we're going to have that. There we go. You just need to remember that. 6.3, R is equal to R0, a to the third. So this equation is consistent with the idea that all nuclei have the same density. What? Okay, so I guess let's just write down density is equal to mass divided by volume. And so that's equal to, fine. So mass divided by, this is a silly question. This is a tautological question, bit of tautology for you. Divided by pi, what are we talking? Pi r cubed, 4/3 pi r cubed. Whoops, forgot the equation there for a sec. Pi r cubed. And so, well, that's proportional to the number of nucleons because the mass is proportional to the number of nucleons. And, well, divided by r cubed. So let's just write that down again. So density is proportional to A over r cubed. And so, what? And so I guess we just put this in the case of, we put that in instead of r, put that in there. Well, that's going to be cubed, but then a to the third all cubed, and so therefore density is just dependent on R0. But I think that's a bit of a tautology, to be honest, because you have to assume that they're all the same density before you actually do make the equation. Silly question, if you ask me. 6.4. The equation is derived from experimental data. Yes, that the density of all particles are the same first. Whatever. Suggest one reason why the constant is derived from this equation is only approximate. Oh, I don't know. I guess we could say that, I guess, we know that mass of a nucleus is not equal to total mass of components because of nuclear shenanigans, total mass of constituent protons and neutrons. I guess we could say that the mass scheme also says, not a perfect sphere. Don't we assume they're a perfect sphere though? I mean, they're not really a sphere anyway because they're just a probability cloud. I'm not getting into that existential nonsense. My word. 6.5. Let's actually do some physics. The measured radius of that is that. Okay, so we have R is equal to 4.02 times 10 to the minus 15. And we have A is 35. Calculate an estimate of whatever. Fine. So R is equal to R, blah, 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 blah. And so we say that R0 is equal to R over A to the third. And so that is 4.02 times 10 to the minus 15 divided by 35 cube rooted. Oh, I guess actually if we're looking for the, oh no, we do want that. Well, we can make life easier for ourselves in a second. Hopefully. How do I do cube root on this blooming thing? Oh dear, I've forgotten how to use the calculator. It's been so long. There we go, and it is meters. Okay, we're also looking for the density. So density is equal to, like we said, total mass over volume. And so that's going to be A times the mass of a proton or neutron, whatever. I'm just going to say Mn for mass of a nucleon, total times the mass of one of those, divided by 4/3 pi r cubed. So that's going to be 35 times by 1.67 times 10 to the minus 27, as you know from your formula sheet. And then we divide that by 4/3. So I'm just going to put the 3 on top there. We think so. 3 divided by 4 times pi times 4.02 times 10 to the minus 15, and that's all cubed. Will you humour me by letting me deal with powers of 10? So that's times 10 to the minus 45, add that onto the top, so plus 45, so that ends up being 18, plus 18 that is. Okay, so let's pop that all into my calculator, providing that I've remembered how to use it. Divide by that, there we go. And I end up with 2.15 times 10 to the 17, what are we talking, kilograms per meter cubed. There we go. Pretty dense stuff. Takes one to know one. 7.1, carbon is used as the moderator. One of the commonly used thingy. We can just use water as the moderator. That's okay. What's the mask scheme say? Beryllium, yes. It's a bit niche, that one. They say heavy water. Doesn't really matter. Normal water is allowed as well. D2O, it says. Oh, that's a nice thing. 7.2, state 2 benefits of slowing down neutrons before fission. Well, for starters, we know that they have to because they reach thermal speeds. We know that they reach thermal speeds such that they can be absorbed by uranium nuclei. The second one, we don't really talk about this, to be honest. But I guess it is true. It's the fact that less likely to escape and cause damage to equipment or living things. Probably should have led with living things, to be perfectly honest. Or let's go with living organisms. They like that word. Okay. Now we have some momentum malarkey, it looks like. 7.3, before collision, after collision. So many MNs and MMs, and oh my days, this is confusing. Why do they have to use these symbols? We're going to be asked to calculate that, are we? Oh, I don't know. Let's have a look. We have a ratio of V to U with the ratio of MM to MN. Right. So the N loses about 30% of its initial kinetic energy. Okay. What is N again? That's U. Okay, so we're looking for U. Right, so lose 30%, so we need to say that we've keep 70%, so that's what we're looking for. We're looking for a 0.7, hopefully, somewhere. Okay, so when M over M equals 12, V over U is equal to, that's bang on, 0.85, isn't it? So if we're looking for energy, then we're looking for the energy after compared to the energy before. And so as we know that energy, kinetic energy, is proportional to V squared, it's half mp squared, we can say that this ratio is therefore equal to the speed after squared divided by the speed before squared. Like we said, ratio, just replace top and bottom with what they are proportional to. And so this actually ends up being the ratio V over U all squared. And so we're just saying 0.85 squared, and that gives us 0.72. So there we go. Kept about 70% of its initial kinetic energy. 7.4, we have the energy afterwards. I'm just going to call that E, methinks. And we have an exponential. So e to the minus by, we're given the constants as well. That's nice. Thermal neutron has kinetic energy equivalent to the average particle. Okay, fine. So we know that kinetic energy is equal to 3/2 kT. And so that is equal to 3/2 times Boltzmann constant times by temperature in Kelvin, 350. Okay, might as well find that out real quick. And that energy ends up being, it doesn't sound like a lot, but it all adds up. So that times 10 to the minus 21 joules. Okay, let's stay accurate for now. Let's go to 4 sig figs. So what are we being asked then? So one neutron has an initial kinetic energy of 1 mega electron volts. Oh, the final kinetic energy, sorry, right. So E0 is 1.6 times 10 to the minus 13 joules. Okay, so then it gets less by that much. Calculate the minimum value of Y required so this neutron becomes a thermal neutron. Okay, it should be fairly easy then. So let's get our e's on the same side. So E over E0 is equal to e to the minus by, and so we're going to log that. So log of E over E0 is equal to just minus by. So y is equal to just the log of these divided by, let's go minus the log of that divided by b. So just popping our numbers in, that's going to be minus log E, that's our final one. So that's divided by the initial, which is just mega electron volt, but in joules, and then divide that by, what are we told B is? 0.73. Okay. And that gives us 23.2. That was a nice question. Fairly easy. Finally, 7.5. Why do we prefer smaller nucleons? Looking at figure 15. Well, it's because smaller and, which one are we looking at? M means smaller ratio of mm to mn. Therefore, smaller ratio of V to U. Therefore, more kinetic energy lost. Therefore, will slow down quicker, or I guess we could say with fewer collisions. There we go. All right, multiple choice. Here we go. We have 1000 watt heater is 75% efficient. Okay, fine. So we're just going to say the power is 750 watts. So temp difference is 75 degrees C or Kelvin, doesn't matter. And the time is 7 hours. So I'm going to say 7 times 3600. And we have the SHC as well, don't we? Classically 4,200. So 7 times. Do you know what? I'm going to leave it as that for now. So what mass of water is heated? Pretty easy if you ask me. So energy is equal to mc delta T, where C is the specific capacity. And so replacing energy with power times time, we end up with this. And so therefore mass is equal to PT over C. I'm just going to put T there. So that's our 750 times by 7 hours times by seconds in an hour divided by our SHC times the temperature difference. So I think we could probably cancel some thousands there. And there we go. Helps a little bit, maybe. Divide that by 42 and 75. And that gives us 60 kilograms. So the answer is C. Question 9. Which can lead to a value for the absolute zero of temperature? So we need to get this and this. And we end up going like that. And so this is our absolute 0 point there. And well, you should know that this has to be temperature because we know that with PV graphs, we end up with this, don't we? It doesn't go down to 0, so we can't really do that. So temperature on the x-axis here, and therefore it's going to be either pressure or volume on the y-axis here. And the only one that's there is Charles's law, and that's going to be volume and temperature. So the answer is C again. Number 10, we have a distance of that, which is an estimate of electrorepulsive force, gravitational attraction force. Okay, similar to before, like we've seen quite a few times already, replace what they are proportional to. Or actually, what they're equal to in this case. Yeah, because there's not going to be any proportionality. So force due to gravity is gmm over r squared. Yeah. You'll see in a second why it works out. And so we're dividing that by, I should have done it the other way around. Let's do it the other way around. So we have Fe equals KQQ over r squared divided by force due to gravity. And so we can just divide that by gmm over r squared. The r squareds cancel, so I don't really understand why we have to have that distance, to be perfectly honest. Because they're just having us on this, throwing a red herring in there. Let's just go. So therefore, it's just going to be KQQ over GMM. And so we know that the charge is the same. So that and then that. But because we're just talking about orders of magnitude, let's actually just go with powers of 10. And so that's going to be K is 9 times 10 to the 9. So that's essentially 10 to the 10. That's just our 1 over 4 pi epsilon 0 times by Q 1.6 times 10 to the minus 19. So I'm going to say minus 19 squared. G is, well, so I'm going to say minus 10. And then times that by, well, 2 protons. And so we're talking about 1.6 times 10 to the minus 27. So I'm going to say minus 27 squared. And so, well, let's just tot all of these up, shall we? And so that ends up being, let's just write that again real quick. So 10 to the 10 times 10 to the minus 38. And then 10 to the minus 10 times 10 to the minus, so 27. So that's going to be 54. Okay, and so once more, so 10 to the minus 28 on top, divided by, what's that going to be? 10 to the minus 64 on the bottom. And so that should give us altogether 10 to the, add on 64 onto the top. So there's going to be 36. Is there one that says 36? Yes, there is. The answer is C. It's one way to second guess yourself by having 3 C's in a row. Data are collected for M, blah, 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 blah. The data show that U is directly proportional to... Oh, okay, fine. So escape velocity, if you can't remember it, always write down, it's just an energy situation. So potential energy is equal to kinetic energy. And so that cancels. And so therefore we can say that V is proportional to, or sorry, V is equal to, let's just go with that first, is equal to the square root of 2gm over r. And so therefore V is proportional to, because g and 2 are constants, so V is proportional to the square root of m over r. And so it looks like the answer is going to be B, because that's the one that has the square root in the form of a half. We broke the C combo. Okay, we have circular orbit, blah, blah, blah. What's the linear speed? So let's just crack out our mv squared over r is equal to gm m over r squared. One of these cancels. We're just looking for the speed, so therefore v is equal, oh, m's cancel as well, whoops, it's equal to the square root of gm over r. But of course, we're above the thingy as well, so we just add on an h to that. That's all it is. So it looks like the answer is B. Oh, here we go. 13, which statement is not true for a geostationary orbit? A, they're above the equator. That's true, so that's not our answer. B, satellite has the same angular velocity. Yes, that's true, because 24 hours, so therefore same thingy. Satellite takes 24 hours to orbit the Earth. That's also true. And so D has to be our answer because it's wrong. Let's just check it. Signals from the satellite can be sent to any point on the Earth during one orbit. No, that's not true. 14. Oh my days, that's a lot of Q's. What's the magnitude of the field strength at the center of the circle? Oh my days. Okay, so we have do you know what? Screw this. I'm just going to put minus, plus, minus, plus, minus, plus. Okay, these cancel each other out. These cancel each other out because they're opposites. And so therefore, these two don't cancel each other out. So the field is going this way due to that and that way due to that. So it's going to be 2 lots of just what the field strength would be due to 1. And so we're going to say, well, it's only 1. Let's do it. So F is equal to K, Q. Oh, they've got 1 over 4 pi epsilon. We need it in this case. So that's our K. Then we need Q over D over R squared. But it is going to be 2 lots of this because we have 2 things creating the field. So I'm just going to put a 2 there. So I'm going to say that, well, first of all, we need to replace our R with D over 2, don't we? So I'm going to say 2Q. I'm going to leave it as 2Q for the time being because I think we're going to end up with a 4 real quick. And so that ends up being D squared over 4 because D over 2 all squared. And so essentially that 4 and that 4 cancel each other. So it looks like the answer is going to be C. 15 2-point charges are separated by that. I don't think we're going to need... I don't think we're going to need that. No, that's fine. So D1 is 200. I don't think the unit matters here, to be honest. The force 1 is equal to 180 There we go. We'll leave it as that as well. It's all going to be relative. You'll see why in a second. So D2 is increased by 400 millimeters. Oh, that's not too bad, actually. Is it? Oh, I don't know. No, that's fine. That's easy. So now it's 600. Easy. We're just looking for the new force of attraction. So force is equal to KQQ over R squared. So therefore force is proportional to 1 over R squared. So therefore F1 R1 squared is equal to F2 R2 squared. Oh, I've mixed up my R's and my D's. Ooh, doesn't matter that much. Okay. What are we looking for? We're looking for F2. So therefore F2 is going to be equal to F1 times by the ratio of R1 squared divided by R2 squared. But I'm just going to combine those. So R1 over R2 all squared. So that's going to be 180 times by R1 is 200 divided by 600 all squared. And so that is 180 times by a third squared. Or in other words, 180 times by a ninth. So 180 divided by 9, that should give us 20. So I think the answer is A. 16, so we have, an electric field. I thought it was magnetic for a sec. Okay, so electron is going up like that. So the force has to be up like that. So that means if this is an electron, then the electric field has to be down, because an electric field shows what the direction of force is on a positive charge, not on an electron. So I haven't even looked at the question yet. Direction of the electric field is vertically down the plane. Yes, it has to be vertically down the plane. So the answer is A. 17, we have this graph of field strength against R. What are we being asked? What's the total area under the curve? Okay, and that's going to 0. Oh, sorry, that's a lie. That's 0 there. That's R there. If it's going to infinity, we have E against R. So electric field strength. I mean, that should probably be fairly easy, should it? Oh, I don't know. Let's have a look at our equations real quick. So electric field strength is equal to, so KQ over R. But then if you multiply by the R, that doesn't really help us. Okay, well, let's have a think real quick, because we know the alternative for field strength is potential gradient. Yeah, this looks more like it. There we go. So if you take this and then we multiply by essentially delta R, then we're just getting delta V. So it looks like we have a potential. And so it looks like the answer is C. 18, which diagram shows the orientation of this polar molecule? Well, it's not going to be sideways, is it? We know it's going to be up or down because they align themselves along the field lines. But if this is going down, if the field is going down, well, if you just have a think about this, what has to be at the top here to create, and the bottom to create this electric field? Well, we know that field lines go from positive to negative, so therefore it's going to be that. So you can just think about which way would the polar molecule have to be aligned to be attracted to these, and so therefore it has to be positive at the bottom, negative on the top. So I think the answer is A. 19, alpha particle, gold nucleus, blah, blah, blah. We have the energy of 9 times 10 to the minus 13 joules. Gold nucleus contains 79 protons. Okay, so we can have the charge of the nucleus as being 79 times 1.6 times 10 to the minus 19, because guaranteed we're going to have to use that. What's the closest possible distance of approach? Why would they? Okay, whatever. Similar to escape velocity, is just to do with energy. And so therefore we say that the, just kinetic energy equals potential energy. So therefore the kinetic energy is going to be equal to KQQ over R. And we're looking for R, so just swapping these two over. So therefore R is going to be equal to KQQ over E. I'm just going to call that E. And so that is our 9 times 10 to the 9 times by the charge of the gold nucleus. Let's go with that first. I'm going to leave the 1.6 for a second, then I'm going to go with times by 2 of the alpha particle. We know that times by that, so I'm just going to put that in there. Bit of a shortcut, but make sure you have that squared on top if you do that. Oh, there's an extra... No, there isn't an extra shortcut, sorry. If it was in electron volts, there would be, but there ain't. I can't be bothered to deal with powers of 10. However, I can see that, oh, maybe I can actually, because, okay, let's do it. So minus 19, so that's just going to be 1.6 squared, and so that ends up being times 10 to the minus 38 on there. And so I'm going to say plus 13 and 9, so that's going to end up being 22. And then combining these at the end here, you can see why I've done this, because the 9 cancels as well. Then just combining these, minus 38 plus 22, so that's just going to end up being minus 16. And there we go, popping that all in. I think it's worth it in this case. What does that give us? Let's say 400 times 10 to the minus 16. And so I can see that there's only one answer that makes any sort of sense there, and it is C. Question 20, we have length of a wire. Oh, F-bill. We haven't really had any magnetic fields in this paper. Huh. Very unusual. So we're looking for B. So we know that F-bill, so therefore B is equal to F over IL. So, but we're told that the current in the wire is increased by 4 amps. The force acting on the wire increases by that. I think they're just trying to throw you off, I guess. Nearly threw me off. Why doesn't it just say when the current is this, the force is this? I guess because, oh, I don't know. Regardless, let's just say that the wire was 0 and then it got increased to 4. And so therefore the force would have been 0 and then it would have been increased to this. So actually we can just pop in our numbers. Just a weird way of doing it. Trying to throw you off. So 3.6 times 10 to the minus 3 divided by 4 times, I tell you what, I can probably just say 150 times 10 to the minus 3. They cancel, and so that's going to be 3.6 divided by, what's that? 600. And so I think it's going to be something like 6. So this is 6 times 10 to the 2. So this is going to be divided by 6. So that's going to be 0.6 times 10 to the minus 3. No calculator needed. 21. Beam of ionized atoms, they go into a magnetic field, circular path, same charge and same speed. So we know F equals BQV, F bev. So they're going to experience the same force if they have the same Q and same V. Okay, so what's the question asking? So A, the force is different. No, we just said that that is not the case. B, the radius of the path followed by the ion is different for each isotope. Yes, because we know that F equals BQV, and that also equals mv squared over r. And so cancelling that, we end up with r, swapping those around. R is equal to mv over bq, and so therefore, because they have different m's, they are going to travel different thingies, different radii. So that is true. C, the kinetic energy increase. No, it doesn't increase, does it? Because they have the same, or rather, I should say, constant speed, because they go in circular motion, and so you get the idea. So that's not our answer. D, the acceleration is the same for both isotopes. No, because F equals ma, and therefore A is equal to F over m, but because they have different m's, that means that they can't have the same acceleration because they have different masses but the same force. So what do we have here? We have flux against time. So we have it. So which one has the EMF? Well, we know that EMF is equal to delta phi over delta t. And so therefore it's equal to the gradient in this case. So we know that, so it's going to be 0 here, and then it's going to be right here, and here it's going to be constant. EMF is going to be constant, but this one's going to be positive, this one's going to be negative. So therefore, well, it can't be C or D, because they're just nonsense, because they're playing on your instincts that you might say, oh, it's increasing and coming back down. No. The gradient is constant when it's going up and coming back down, so therefore it has to be that. However, like I said, it's going to be minus on the way down, so it's going to be a negative EMF. So the answer is A. 23, we have the distance between the wingtips, and we have a speed of 100 meters per second, and we have flux density of 2 times 10 to the minus 7 Tesla. What's the EMF? EMF is equal to BLV. If you can't remember that, then have a look at my video and see if you can derive it. If you really want to see me derive it now, fine, I'll do it for you. So EMF is equal to rate of change of flux. But we know that flux is BA. I'm just going to drop the deltas here. And we know that the area is equal to, well, just the length times the width. And then that's divided by time. And then you take one of these divided by time, and that gives you a speed, doesn't it? So that's where BLV comes from. Easy peasy. So BLV, so there's going to be 2 times 10 to the minus 7 times by the length of 30 meters times by the speed of 100. So yeah, I think it's going to be 6. That's the only one that it can be. And so, so that's 2 times 30 times 100. And so that's going to be 6 times 10 to the minus 4. And so there's going to be 600 microvolts. There we go, 24. Circular coil with a radius of that. So we're going to have the radius. So we might as well do that. So pi r squared. Let's leave it as that for now. And n is 200. Coil rotates at 50 revolutions per second. Okay, so that's frequency is 50 hertz. So let's write this down. So it's going to be pi times 0.1 squared. Or in other words, pi times 10 to the minus 2. How's about that? Flux density is 0.2 Tesla. What's the EMF induced in the coil? EMF is equal to ban omega, or the max EMF rather. If it's any other one, that we add in the sine omega t, but we're not dealing with that here because we're looking for the max. Or I could just put epsilon 0. And so that's going to be just 0.2 times by pi times 10 to the minus 2 times by 200. So I'm just going to say 2 times 10 to the 2. Look at that. Look at that there. That's a good reference. I wonder if anybody can get that one. Times by 2 pi f. And so 2 pi times by 50. And so that is 0.2 times by pi squared times by, oh, I've lost track, times by 4 times by 50. And so this ends up just being 40 pi squared. And what do I end up with? 395 volts. So the answer is D. 25, radioactive waste. Why is it stored underground? Alpha particles. No, it's not alpha particles. So it's not B and it's not A. Because alpha particles will be stopped by anything, won't they? Is it C or D then? Well, it's gamma radiation from nuclides with a... See, I don't think this is a very nice one, but because it lasts for a long time. But I guess if we're talking about workers, so we are talking about workers. So we want to limit dose, so limit exposure to high activity. And so if it has a high activity, that means that it has a high decay constant because it's decaying very quickly. And so therefore we are talking about D. I don't like these questions though. Alpha particle, thin glowed foil. What statement is not true? Okay, foil is thin enough to assume that alpha particles are deflected only once. Yes, that is true. B, nuclei are more massive than the alpha particles to be deflected by more than 90 degrees. Yes, because if that wasn't the case, then the particles would get deflected. That's a bit of a weird one though. So if the nuclei were lighter, then it would be the nucleus that moves out of the way, as it were. And so, as the alpha particle comes in here, instead of going like that, then it would go like that, while the nucleus moves a little bit like that. So it would be deflected less. Fair enough. Number of alpha particles deflected backwards is greater. Well, that's just nonsense, isn't it? Because we know it's about 1 in 10,000, if not less than that. And so that's our right answer there. D, let's just check it. Deflections of alpha particles by electrons are much smaller than... Yeah, of course that's true, because they just barrel right through the electrons. Never really talk about that. Okay, transformer, 230 volts AC supply. So V1 is 230. 90% efficient. That efficiency always is to do with power. So we are talking here V1 I1 is equal to V2 I2. That would be true if it was 100% efficient, but the second coil only gets 90%, and so it's therefore 0.9 times V1 I1 on the left there. All we have to do is rearrange this. We're just looking for I1. So therefore, rearranging this, we end up with I1 is equal to V2, I2 over V1. I'm going to pop those there, and you'll see why. It's because, oh, I see, that doesn't really make a difference. Whatever. There we go. So I'm just going to say that that is 12 times 3 divided by 230 times by 0.9. And I end up with 0.174 amps. So the answer is C. 28. Random nature of radioactive decay. Never possible to predict when a particular nucleus will decay. Yes, that's true. So that's our answer. Let's just check the other ones. B. Oh, for goodness sake. Oh, well, that's just nonsense. So it's nothing to do with pair production at all. Well, that's just nonsense because it's nothing to do with what particle is being produced. It goes for alpha, beta, or gamma, doesn't it? C. The approximate time taken. No, that's nonsense. And then D. Approximate thickness. Oh, my days. Easiest question ever. 29. Radiation is used to see what? It's going to be B, man. Because, you know, some beta minus can go through, isn't it? Of course that's the case. You know that from year 9, for crying out loud. These questions are getting super easy towards the end. They ran out of hard questions, finally. Tritium is a radioactive nuclide used in exit signs. I didn't know that. That's cool. Okay, manufactured, so we have the activity to begin with is 37. I'm not even going to bother with megabecquerel. Megabecquerel. After 10 years, again, I'm not even going to bother with that because it's all relative. And then we have the activity is 21. Okay, so we are going to look for the decay constant, methinks. So we know A over A0 is equal to E to the minus lambda T. And so therefore we're going to log both these. So we end up with log of A over A0 is equal to minus lambda T. We're looking for lambda, so therefore lambda is going to be equal to minus log of all that over the time. And so that's going to be minus log of 21 over 37 divided by 10. And that gives us a lambda of 0.057, let's say. Or actually, we should be more accurate because look at those answers. 12, 13, 16, 17. They're very close. Let's go with 6, 6 then, shall we? That's yes to the minus 1, not that we care that much. And so therefore, we're then going to go for the second part, and that is A equals A0. So 15 years after it was manufactured. Yeah. So E to the minus lambda T. And so that's equal to 37 times by E to the minus 0.0566 times by 15, because it's now 15 years. All right, what do we end up with then? So 15.8. So I think the answer is 16 megabecquerel. Good, thank goodness for that. 31, mass of fuel decreases by 4. Do you know what? I'm going to say delta M by T is equal to 4 times 10 to the minus 6, and that's kilograms per hour. So we're looking for power. So therefore, we're going to have to turn this into seconds. So divide that by 3,600, and that'll give us the mass change per second. And so that's 1.11 times 10 to the minus 9 kilograms per second. So let's have a look. We're looking for power, and we know that's equal to energy divided by time. And we know that the energy in this case is equal to mc squared divided by time. And then look at this. We have delta M over T. We have M over T there. So that's what we're looking for. So we're going to say 1.11 times 10 to the minus 9 times by 3 times 10 to the 8 squared. Or in other words, 1.11 times 10 to the minus 9. I think I know the answer already. I think it's going to be B. But let's just have a look. Times 9 times 10 to the 16. That just ends up being then 7. And so this ends up being roughly, I think, 10 times 10 to the 7. Or in other words, 1 times 10 to the 8 watts. And so I think the answer is B. All right. Yes, I am. Finally, question 32. Again, the first time I did this question, I didn't follow my own rule, which is really dumb. And that is, as soon as you see a graph of activity against time, you know the first thing you want to do is find the half-life. Easy. And so we're going to go from, why not, 14 to 17. That gives us a nice time, and I think that's going to be 30 seconds. So half-life is that. And so therefore, well, we're looking for n, aren't we? And so therefore we're just going to say lambda n. We don't need the minus in there because we're just looking for the magnitude. And so therefore we're going to say that, well, we know that the decay constant is equal to log 2 over the half-life. So therefore we can just say that activity is equal to log 2 or n log 2 over the half-life. We're just replacing lambda. We're looking for n. So therefore we're just going to say n is equal to activity times the half-life divided by log 2. So that's going to be 14 times 10 to the 6th. That's 14 megabecquerel. And then we're going to multiply that by 30 and then divide by log 2. And that gives me 6.06 times 10 to the 8. And that is just a number. So it looks like the answer is going to be D. So I hope you found that helpful. If you did, please leave a like and a comment and check out the channel to see more videos going through past papers and videos going through whole papers in like an hour each. I'll see you next time.